One interesting aspect of Prolog is that there are different ways to read and understand Prolog code. For example, we can read Prolog code declaratively. This is when we ask what is true and what follows from what, and read the code with these questions in mind. As another approach, we can read Prolog code selectively. This is when we ask, what can we say about fragments of the code? That is, when we consider only a subset of the code. And as yet another approach, we can read Prolog code procedurally. This is when we ask, how is the code executed? So a procedural reading is close to how a machine interprets the code. And these approaches have different advantages and drawbacks. For example, the meaning of Prolog code is best understood by declarative reading. And selective reading is great for generating explanations, manually and also automatically. And operational aspects, such as, for example, performance properties, can be understood by procedural reading. However, procedural reading is usually too hard to apply, and also isn't able to capture the full generality of Prolog programs. And these aren't even the only ways to read Prolog code. For example, we can also read Prolog code informally, where we simply express in our own words what the code means. For instance, let's consider the predicate list length. And as the name suggests, this predicate relates a list to its length. So we have list length holds, of course, for the empty list. And in that case, the length is 0. And further, it also holds for a list with exactly one element and tail ls. And in that case, the length L of the entire list is in a certain relation with the list in the first argument. Namely, if the length of the tail is L0, then the predicate is true if L is L0 plus 1. And that's it. And we can read this definition informally, for example, as the length of the empty list is 0, and the length of a list with one element and a tail is the length of the tail plus 1, right? So this informally describes what we just stated more formally with a Prolog program. And there are clearly some disadvantages to an informal description, because first, it's informal, so we can't directly use it to write test cases, for example, or to execute it. And also, informal reading can make it quite complex and awkward to refer to the things that occur in the description. For instance, we mention here a tail, and here we refer to that same tail. So maybe instead of the, we should have said that. And to make extra clear to what we are referring, maybe we should say a tail ls and then refer to ls for clarity. So the clearer we want to make an informal description, the more similar it will look to a Prolog program, especially if there are many entities involved. Another way of reading Prolog code is called declarative reading. For instance, we can read the first clause as list length holds for the empty list and 0. This clause consists of only a head and has no body, so this is a fact. And we can read the second clause as an implication. If list length holds for ls and l0, and, so the comma here denotes the built-in predicate conjunction and is read as and, L is equal to L0 plus 1 holds, that is, if L is the arithmetic result of L0 plus 1, then, so colon dash is meant to denote an arrow from right to left, then list length holds for these arguments. So this second clause has a head and a body, where body implies head, and this is called a rule. So we've now read the program in terms of what holds and what follows from what. And this way of reading the code does justice to the full generality of the code, because we can use the code in several directions to generate, to complete, and also to test solutions. And this way of reading Prolog code is also called concluding reading. And this is a very important way of reading Prolog code, because the beauty of Prolog is that by just stating what holds and what follows from what, we can use Prolog to automatically derive logical consequences. For instance, let's ask, does the relation hold for any arguments at all? This is called the most general query, because it doesn't place any other constraints on the arguments. And when we post this query, then we get a solution. Yes, the predicate holds, for instance for the empty list, and 0. So this is a logical consequence of the program, which isn't surprising because there's a fact that states exactly this. And on backtracking, we get another answer. This states that for any list ls with exactly one element A, the relation holds if L is 1. And A can be any Prolog term, so this answer in fact compactly describes an infinite set of concrete solutions. And on backtracking, we get another answer, and another, and so on. And each of these answers is a logical consequence of the program. So for the most general query, our example program works very nicely, and it fairly enumerates lists of all lengths. And as another sample query, what about a concrete list, say ABC, so a list with 3 elements? Then when we post this, we again get a concrete solution. The length L of this list is 3. So the program also works very nicely in this more specific case, to compute the length of a given list. And as another example, let's ask in the other direction, namely, suppose only the length is known. So we ask, are there any lists of length 3? And yes, of course, there is a list of length 3. In fact, there are infinitely many lists of length 3, and this answer compactly describes all lists of length 3, because each of these variables, a, b, and c, can be instantiated to any term. So this answer is correct. Now, what about other answers? Well, on backtracking, we get non-termination. So from this interaction, we can't tell whether the program describes any other solutions too, because Prolog doesn't tell us anything beyond the first answer. It doesn't say that there is another answer too, and it also doesn't say that there is no other answer. It simply doesn't terminate. And to focus exclusively on termination properties of the program, let's add the goal false at the end of this query. So declaratively, this certainly can't hold, because the built-in predicate false never holds. So from a declarative point of view, this conjunction is equivalent to false. And if this query produces any answer, then the answer must be false. So the only thing that can be observed here is termination. And I mean universal termination. This means not that the query produces a solution, but that the query terminates after the solutions, if there are any, are found. And when we post this, we see again that this query doesn't terminate. Whereas, of course, we would like this query to terminate, because we, of course, know that all lists of length 3 have the same shape, and that the shape can be compactly expressed in Prolog as a list with 3 variables. So ideally, in this case, if we ask for all lists of length 3, we'd like to get exactly one answer and a clear statement from the Prolog system that there are no other solutions. So how can we do this? First, why do we observe non-termination with this version of the predicate? And this is where selective reading helps, because selective reading can explain the non-termination. Selective reading is also called program slicing, and as the name already implies, it works by considering fragments of the original program. And ideally, fragments are small and easy to understand, and at the same time, let us draw interesting conclusions about the original program. And there are several forms of program slicing. For example, we could simply take away one of the goals and therefore make the program more general. And to explain non-termination, failure slicing is especially useful. Failure slicing is a special case of program slicing, and it means that we insert the goal false at some points in our definition. For instance, suppose we turn this fact into a rule and we say the head holds if false holds. Well, that's of course never the case, because false, as the name suggests, is always false. So in effect, this means that this rule may just as well be left out entirely, because the body can never be true. So we use strikeout text to indicate that we can totally ignore this rule. And we can insert false also at other places in our code. For instance, let's insert false here. Then this means that everything that follows can be ignored, because false never succeeds. And so Prolog's default execution strategy never proceeds beyond this point. So we can strike out all goals after this point, because they have no influence on the execution of this program. Now, let's try our sample query with this modified program. So when we post this query, we again get non-termination. So the remaining fragment by itself already causes non-termination, and adding a clause or changing anything in the strikeout parts can't prevent this non-termination. This means that the visible part must be changed to prevent the non-termination. So that's a very strong property of this fragment, because if this fragment by itself already doesn't terminate, then the original program also doesn't terminate. So in other words, we have produced an explanation for the non-termination of the original program. And the really great thing is that the explanation is very simple and easy to understand, much simpler than, for example, a trace. And also, the explanation stays syntactically very close to the original program. And the explanation is in fact also a Prolog program. So there's no need for learning an additional formalism, such as a proof tree, for example. And moreover, such an explanation can even be automatically generated. So what can we do to improve termination properties of the original program? Well, one thing we could certainly do is to exchange these goals, right? Because from a declarative perspective, changing the order of goals doesn't affect the meaning of rules, because conjunction is commutative. So let's try our query again. Well, it still doesn't terminate. So what else can we do? First, what about trying a different sample query? Say, are there any lists with length -1? And when we post this, we also get non-termination. However, we'd of course like the query to fail, because there are no lists with length -1. So let's state this explicitly. We simply state this as a constraint on the length L, because that's how we program in Prolog. We state what holds under what conditions. So we state that the length L must be greater than 0 for the second clause to apply. Now, when we post this, we still get non-termination. But declaratively, we know that this can't hold and therefore must be false, because we just stated that for the second clause to apply, L must be greater than 0. And considering all clauses, L must be greater than or equal to 0 for the relation to hold. It can never be less than 0. So from a purely declarative reading, where we consider what holds under what conditions, we conclude that this must be false. But for procedural reasons, it still doesn't terminate, because procedurally, the order of goals matters. So a procedural reading takes into account the actual execution strategy. And by default, Prolog considers the goals in the order in which they are stated. So for example, in this concrete case, to prove the head of the rule, Prolog first tries to prove the first goal, then the second goal, and then the third goal, in the order in which they appear. And the execution strategy also provides the semantic justification for failure slicing, because if we insert false here, then all further goals can be ignored, because Prolog considers the goals in the order in which they are stated. And if one of the goals fails, then Prolog doesn't consider the other ones. And in this case, we already know that the remaining fragment doesn't terminate, because the remaining fragment has the same termination properties as the version of our predicate that we've just tried, where the last goal wasn't there at all. And therefore, adding further goals at the end can't prevent the non-termination. So one consequence we can draw from procedural considerations and also from failure slicing is that if we want to improve termination properties of our programs, then we place terminating goals early. That is, we place terminating goals before fragments that cause non-termination, because only then do they have a chance to improve termination properties. And there are many goals that always terminate. For example, CLP-Z constraints always terminate. And therefore, to improve termination properties of our programs, we place CLP-Z constraints early. So for instance, the last goal is a CLP-Z constraint, and so we exchange the last two goals to put the CLP-Z constraint before a fragment that causes non-termination. And declaratively, that is, only considering what is being described, this changes nothing. But procedurally, it makes a difference, because when we now post our sample query, then it indeed terminates. And it also correctly tells us that there is no list with length -1. So this works very nicely now. And further, when we ask for lists of length 3, then we get an answer as before, and on backtracking, we now get false. So Prolog tells us that there are no other answers. So the query now terminates, which is great. And we can improve the program even further by making it deterministic, so that no redundant choice points remain. And I leave this as a small challenge. Now, why are these methods of reading Prolog code important? Well, Prolog code can be interpreted with different execution strategies. And some of these strategies are only now becoming widely available. For instance, tabling is now available in several Prolog systems, and it will become available in even more systems in the future. And tabling is also known as SLG resolution. So it's a specific variant of resolution that differs from Prolog's default resolution strategy. And of course, there are also other ways to interpret Prolog code. And in general, procedural reading is simply too hard, because it requires to understand the precise steps that Prolog performs. And that in itself doesn't count as a strong argument against it, because many worthwhile things are also hard. The key drawback of procedural reading is rather that it's also quite pointless in addition to being hard. So all effort we put into it is mostly wasted, because when we slightly change the program or the execution strategy, then we have to trace the steps again. And also, a procedural reading, as already mentioned, doesn't do justice to the different modes in which we can use Prolog code. And it encourages a procedural view that takes us away from the true generality of Prolog. So, in that regard, procedural reading is also quite counterproductive and prevents us from using Prolog to its fullest potential. So, to fully understand the meaning and the properties of Prolog code, we need better techniques to read the code. And in particular, we need declarative and selective readings, because these readings let us reason about the code in a very elegant and simple way. And these methods are quite generally applicable. In particular, they work for the pure and monotonic subset of Prolog, which is a very important and Turing-complete subset of Prolog. And we'll discuss this subset in more detail on another occasion. For now, I only state that Pure means, informally, that the program has the properties we expect from relations. So, for instance, a pure program doesn't perform destructive changes and doesn't have side effects. And monotonic means monotonicity of the inference relation, like in logic. This means, for example, that adding a clause or removing a goal makes a program at most more general, never more specific. And there are many predicates that do have these properties. And one of our goals is to increase this pure monotonic core of Prolog, so that over time, more and more Prolog programs can be read declaratively and selectively. Because, of course, we want to be able to easily understand Prolog code. And we also want to use methods that help us to improve our programs. And to make our code amenable to declarative reading and to selective reading, we stay in the pure monotonic core of Prolog.